ready to start the class. So welcome everyone to CS224W. I hope everyone had a good Thanksgiving break and ate a lot of turkey or any synthetically grown equivalent or something like that. So today I'm super excited to be able to present Petar Veličković, who's a senior staff researcher at DeepMind and affiliate lecturer at the University of Cambridge in UK, and also an associate of Clare Hall at Cambridge. Petar is one of the pioneers of graph machine learning. He is the author of Graph Attention Networks, as well as many other very popular and influential papers, for example, the Deep Graph Infomax. Today, he's going to talk to us about machine learning on graphs and generalizations beyond graphs, and thinking about the broader area of geometric machine learning. The way this is going to go is Petar will give about an hour and 10-minute lecture. I encourage people to ask questions using the Zoom Q&A feature. There will be a break in between when we'll be able to answer the questions, and then at the end of the lecture there'll also be ability to further ask questions. So with this, Petar, the floor is yours, and thanks again for coming, and very much looking forward to your lecture.
Perfect. Thank you very much, Jure, for that fantastic introduction, and thank you for having me. It is a great pleasure to be able to speak at CS224W. It's a course that I've personally followed some years ago, and yeah, it just feels pretty surreal to be able to speak on the other side of the virtual lecture theater. So today, as Jure mentioned, we will be talking about geometric deep learning. And before we even start diving into the aspects of geometric deep learning, I want to give a little bit of a historical motivation for why might it even make sense to connect geometry with deep learning, and what do I even mean when I say geometry, and so on and so forth. So for me to be able to show this to you, we are actually going to go back in time, way back in time, to the days of Euclid, around 300 BC. So as you might know, Euclid is the main inventor of what is known as the Euclidean geometry. And for many, many, many centuries, this was the way to do geometry. Like when you said you were doing geometry, it was basically synonymous with the work of Euclid and the specific postulates that Euclid used to unify his explanation of geometry at the time. This all drastically started to change around the 1800s, when suddenly there was a massive influx of new types of geometry, such as the hyperbolic geometry of Lobachevsky and Bolyai and the elliptic geometry of Riemann, where basically a huge amount of authors have suddenly realized that if they assume that one of Euclid's postulates is not true, and they try to go on and derive a contradiction, what they actually end up deriving is a completely new set of self-consistent geometries that turn out to be really good at explaining phenomena over different kinds of surfaces. So what actually happened in the 1800s is that it actually became a very exciting time to be studying geometry, because there were all of these different concurrent ideas with their own terminologies, and all of them were in principle self-consistent and good at explaining phenomena in different settings. So one very natural question that arises as a result of this is, as a student going into the field of geometry, what is the one true geometry? What should you be studying? Is there any of these that is inherently better than the others? And the direction towards an answer to this question came several decades later through the work of a young Bavarian mathematician by the name of Felix Klein, who at the time was just appointed for a professorship at the University of Erlangen in Germany. And what he proposed there is something that afterwards became known as the Erlangen program. And it actually suggested that all of these different geometries can be unified using a single lens of invariances, symmetries, and group theory. So this idea allowed you to think about all of these various geometries by just pre-specifying what's the domain that you're information lives on, and what are the symmetries that that data must respect. And we will talk about all of these in a lot more detail throughout this lecture. But it cannot be understated how much this program had massive of an impact, not just on mathematics, but massive spillover effects in other sciences as well. So through several follow-up works, and primarily through formalization of Illy-Cartan in the 1920s, this Erlangen program had a super strong impact on geometry itself, because there was no longer the need to hunt for the one true geometry. But besides mathematics, it also had a massive and impactful spillover into physics through the work of Emmy Noether. And Noether's theorem specifically states that you can use these principles of symmetry to derive all the laws of conservation in physics. So essentially, whereas previously you required painstaking amounts of experimental data, this principle allows you to just derive these kinds of results from just assuming that the outcome of an experiment is invariant to the time of day when you take it. And the direction situated by Noether's theorem even enabled us to classify several of the elementary particles as part of the standard model in physics. And also, the Erlangen program had a massive spillover effect in theoretical computer science, where category theory is one of the very popular ways in which you can talk about concepts in traditional computer science. And specifically, in the words of the creators of category theory, you can see it as a continuation of Felix Klein's work. So this program clearly had a huge spillover effect all over science, and looking at geometric concepts from a unifying lens turned out to be quite an impactful concept. Now, fast forward to, say, the year is 2020, and you are a deep learning researcher, and you look around the archive and you see what kinds of papers and ideas are floating around. You will actually see that people are coming up with various kinds of impactful deep learning architectures. So ConvNets, GNNs, transformers, RNNs, and so on. And usually these architectures are followed by certain kinds of potentially bombastic statements, like everything can be represented as a convolution, transformers use self-attention, attention is all you need. Everything can be represented as a graph, therefore graph neural networks are the way to go. And long short-term memories are Turing complete, so why would you ever need anything else? So if anything, we might say that the field of deep learning circa 2020 is feeling a lot like geometry in the 1800s. And if history is to teach us anything, now that everybody is asking and laying claim to the one true architecture, then basically the way forward will be to try to study some of those geometric principles that worked so well back then for mathematics. Now, one thing that is quite important to note here, and could be quite useful to those of you taking this particular course, is that indeed, if you squint hard enough, many neural networks of interest can be seen as message passing over a graph structure. Here are given some specific graphs that arise from fully connected convolutional and recurrent neural network layers. And further, there's a lot of good motivation to study data on graphs, because most of the data you receive from nature is inherently structured like a graph. And therefore, there is a fair chance that whatever ends up being the one true way to parameterize architectures, GNNs will likely play a part in it. So that's a very good motivation for why you should be taking this particular course. But in order for us to formalize how could GNNs play a part in the answer, we need to understand them beyond just the concept of permutation equivariance and invariance, which you have seen throughout this course. And with that in mind, now it's actually our turn to study geometry. So my name is Petar Veličković. I'm a staff research scientist at DeepMind and affiliated lecturer at Cambridge. And alongside my co-authors, Michael Brownstein, Jean Bruna, and Taco Cohen, we have set out to do exactly this. And we have recently written a proto book on the principles of geometric deep learning. And today it is my great pleasure to be telling you about some of the findings from this blueprint, focused specifically on graph neural networks and how we can use their prescriptions to advance graph neural networks for the future. So before we dive into graph neural networks specifically, or geometry specifically, I'd just like to give a quick refresher as to why do we even care about introducing geometry into machine learning models. And that is the fact that high dimensional learning, which deep learning concerns itself with, is a fundamentally hard problem. So even if you, well, as you might know, most of machine learning and deep learning nowadays can be reduced to a form of curve fitting, figuring out parameters of a model to fit particular data in a particular high-dimensional space. The problem with this particular setting is that even if you restrict your class of possible functions to fairly simple ones, such as, say, functions respecting one Lipschitz continuity, so they're not allowed to change too drastically around any particular point, still it is easy to construct examples for which, in order to perfectly, or well, to fit reasonably well a function of that particular class from training data, which are given here in red points, you can easily construct examples that will require exponentially many training samples as you increase the number of dimensions you're learning in. So effectively, this is known as the curse of dimensionality, and shows why the very essence of learning in high dimensions is a potentially cursed problem. And you might say, okay, if high dimensional learning is tricky, let's just try low dimensional learning. Let's try projecting our data to a low dimensional manifold and then try to learn from there. Well, in some cases, for example, for classifying MNIST digits, this might be enough. But as you can see here, I've shown the outcome of applying, say, a simple low-pass filter to MNIST digits. You can see that they get very blurry and they lose a lot of detail. So the moment you need to do something a bit more complicated than predicting what digit I'm looking at, suddenly the fidelity is not good enough for these kinds of problems. So high dimensional learning is inherently cursed, and unless your data manifold is reasonably linear, low dimensional projections don't necessarily help. So what can we do with this particular setting? And to see what we can do, we will introduce some very important mathematical concepts of symmetries, groups, and invariances. So specifically, the way in which we try to fix the problem in deep learning is by injecting some additional assumptions to the class of functions that we're fitting, such that they respect the geometry of the underlying problem. And we often refer to this injected assumption as an inductive bias. Specifically, what it does is it restricts the space of functions in our hypothesis space to the ones that respect the underlying geometry. So basically, now you have a much smaller set of functions to fit, and as a result, hopefully your high-dimensional problem is no longer as cursed as it used to be. A few popular examples of geometric biases you can inject. Image inputs should be, in principle, processed independently of any shifts applied to them. Data which lives on spheres, like the smiley face, should be processed the same way no matter how I rotate it. It's along the sphere, it's still the smiley face. And in the case of graphs, which is particularly relevant to this course, you should process two graph structures exactly the same if they're isomorphic, regardless of how you choose to present that graph to the computer. So here you have two graphs where if you stare close enough, you will see they're actually exactly the same graph. And any graph neural network that operates over them should give the same results for those two graphs. So these kinds of restrictions can be particularly powerful in simplifying the prediction problem that we have to do. And now we will try to take this piece of intuition and try to make it a bit more formal. And it turns out that this can be actually done. And I will first present a few mathematical points that just so we all agree on the notation. We assume our data lives on a particular domain omega, and therefore the individual elements of this domain could be pixels if we're looking at images, or nodes if we're looking at graphs, and so on. And because in deep learning, we're usually interested in representations and learning features of these parts of the domain, we will assume a feature space C to be stored in every element of the domain. So since we're doing basically learning representations as real vectors, for us, C will usually be the k-dimensional space of real vectors. And once we have these two components, we can say what it means to featureize the domain. Especially, we can define the set of all feature functions, capital X, which take elements of the domain omega and return the corresponding feature vector assigned to that particular pixel or that particular node. And as you're probably well familiar by now with graph neural networks, graphs are usually a discrete environment. So you can usually think of these feature functions as just a feature matrix, which is an n by k matrix, where n is the number of nodes in your domain and k is the dimensionality of the features that you have on the nodes. So this is basically a node feature matrix by analogy to graph nets. Now, the first principle that we're going to use to simplify our class of neural networks used to fit the problem is the concept of symmetry groups. Now, what do I mean by symmetry? So symmetry is any kind of transformation. In the case of images, that would be a shift. In the case of graphs, that would be a permutation that would leave the underlying object invariant, that is unchanged. Now, the very fact of me saying this, that it must leave the object unchanged, immediately implies a few properties that these transformations must have. First of all, they must be composable. So if I have two functions that both leave the object unchanged, I can apply the first one, then apply the second one, and I will get, as a result, another new function that leaves the object unchanged. If in any other case, I would have had to lose some information. Also, this implies that the function must have an inverse, because if there's no inverse, I've dropped some information while doing my function. And it also implies that the identity function, one which doesn't modify any parts of the domain, must also be a symmetry by definition. And when you group together all of these different properties that these transformations must have, you'll end up realizing that they respect the structure of a very elegant mathematical object known as the group. And the elements of these groups are the domain transformations. So some function g that takes elements of the domain omega to different elements of the domain omega. And in case you need to brush up on your group theory, I have provided here just a recap of all the axioms that a group must satisfy. So associativity, identity, inverse, and closure. But I feel like all of these things are much better visualized with a concrete example. So here you can see the example of the domain omega of triangles, where you're featurizing the three different corners of the triangle. And the transformations you can do to the triangle that leave the underlying object unchanged are rotating the triangle or horizontally flipping the triangle, denoted here by R and by F. And these two operations together form a symmetry group across all possible ways to modify the structure of the triangle without changing the underlying object. So what's important to note here is that the rotation and flips themselves are elements of the symmetry group G, and the individual nodes of the triangle are elements of the domain omega. So in this particular highlighted case, the rotation R, which is highlighted, takes the domain element node, which currently has a 1, from the top corner to the left corner. And you can reason about more complicated structures using these kinds of tables, but it's usually easiest to visualize in the case of these small triangles. OK. Now, we're not just interested in how these things affect the domain. We actually care about how they also affect the data. So for that, we define the concept of a group action. So when I have a group element G and a domain element U, I will define the group action of G over U, which performs the corresponding effect on the data. So something like translating or rotating an image or permuting a set. And that's usually an operation we want to be resistant to. We will be specifically only interested in group actions that are linear, in the sense that when I apply my group action to any linear combination of node features, I can push in the group action as deeply as possible, and this doesn't change the result. So if I want to, take a linear combination of some node feature vectors and then permute them, it's the same as if I first permute both of those node features appropriately and then perform the linear combination. The reason why we will be interested in just those is because that's usually enough to express the full strength of deep learning, because the way nonlinearity is typically injected in deep learning is not through these complicated constructs, but actually just through pointwise activation functions. And also because it will very conveniently allow us to talk about these group actions purely in the language of linear algebra. Specifically, there will exist this map rho, which will take individual group actions G and give me a unique n by n invertible matrix, which represents that particular group action, so that when I apply that matrix, multiplying it to the data, I will get the same effect as if I did the group action in the first place. This will be very useful because for deep learning, we want to stay within the realms of linear algebra, and this rho map will allow us to do exactly this. And I'll give some very concrete examples of rho as we proceed throughout this lecture. And once we have this concept, we can now finally say what it means for a function class, like a neural network, to be resistant to these symmetries in the data. So first, we define the concept of GInvariance, where I'm mapping from a signal given on my domain, so x of omega, to some prediction over the entire domain. And the function acting on this is GInvariant if no matter what group action I take from G, I will get the same results. So any kind of group action on the input will not change the output of the function. So one classical example of this is image classification, where the output class, which is in the image, likely won't depend on how that image is shifted. Now, this is very useful if we want outputs on the level of the entire domain, like a prediction for the whole image. But if we want predictions over individual nodes of the domain, like individual pixels of the image, then we actually don't want invariance, because that would destroy or make it hard to recover the identities of the individual pixels. So in this particular case, we might actually be interested in something a bit more fine-grained. So a function class that takes signals on omega to different signals on omega, so all the nodes are still preserved. And we define the concept of G equivariance. If no matter what group action I perform, it will change the output, but it will change it in a predictable way, such that it doesn't matter if I do the group action before or after applying my function. So in this particular case, the input and the output of the function are affected by the group in the same way. So in the case of image segmentation, where you have to classify every pixel of the image for existence of objects, and you have a particular segmentation mask coming as the output of your neural network, if your function is shift equivariant, then any shifts I perform in the input image must be also applied to the resulting mask. So the mask must follow any shifts in the input. Now, using these two principles of invariance and equivariance, we can strongly restrict the class of neural models that we're dealing with and hopefully make our problem more tractable. But there is another constraint which is really important in practice to make these models well behaved, because we discussed resilience to these kinds of very pure symmetry functions. But in principle, nature will not always act on data in a way that is symmetry. So imagine you have this picture of a house. And OK, a perfect symmetry, like a shift, might just shift that house to a different part of the image. That's still the same house. That's great. But in reality, natural inputs are susceptible to noise and different kinds of distortions. So you might end up with a transformed house that's not just shifted, but also, distorted in a weird way, so that it's not a perfect symmetry transformation anymore. But you should still want your neural network to reasonably classify those things as houses without drastically blowing up and giving you nonsense answers. And I won't get into the detail of what we've concluded for these kinds of problems. But what we derive in our work is that to accomplish this level of so-called geometric stability, it is highly beneficial to compose operations that are very local in order to model larger scale ones. And this is because local operations will not globally propagate errors. So, any kind of mistake that happens in the input because of a distortion will be contained within a small region around a particular point of the domain. So this is part of the reason why many modern convolutional neural networks are designed with only 3x3 kernels, which are very small, but then we make them very deep to propagate information. And accordingly, what we would want is to be able to support a notion of locality in our layers. So it's not just enough for them to be invariant and equivariant. We might also want them to, with respect to the domain, only act around some neighborhood of individual points. And as you've probably seen during this course, this is also very important when designing graph nets. So using all of these components together, we can arrive at what we call the blueprint of geometric deep learning. So we've described a few very interesting building blocks that we can use. So we might want to take these equivariant layers that take a signal on the domain to a different signal on the domain, such that we are equivariant to the individual group action, and they should also respect some kind of locality, ideally. Then we also have the GInvariant functions. If for any reason we don't care about outputs on individual nodes, but we want to predict in an invariant way across the whole domain. Another element that we need for deep learning is to introduce some kind of nonlinearities. And in deep learning, we typically do that by pointwise activation functions like ReLU or sigmoid, which we can apply on every single element of the domain in isolation. And lastly, one thing that I will not cover in detail here, but it is quite important, especially if you want hierarchical data processing, is to also introduce some notion of local pooling in your domain, such that you modify your signal from the original domain to a signal on a slightly coarsened domain omega prime, which is in some way contained in the original one. So if you take these four building blocks, equivariance, invariance, nonlinearity, and pooling, and you combine them together, you actually end up with a very generic blueprint for building deep learning architectures. So you have a stack of equivariant layers followed by nonlinearities. And then if you want, you can also make the domain coarsened by applying pooling layers. And then finally, if you want predictions on the level of the whole domain, you do some invariant function to predict an output over the whole domain. And this turns out to be pretty much all you need to build the architectures that are all you need. And we didn't just hypothesize this, we pretty much directly derived it. For many class of our fan favorite neural networks, we can derive them using this blueprint if you have the right choice of the domain and the right choice of symmetries that you want to be resistant to in terms of invariance and equivariance. So all the fan favorites like CNNs, GNNs, deep sets, transformers, and LSTMs are derivable using this blueprint. But you can also discover some very interesting extras in the middle, like spherical CNNs and mesh CNNs that we will also be talking about. So hopefully, throughout the remainder of this lecture, I'll be giving you some more interesting insights into how exactly all of these results have come to be and what they could mean for development of GNNs specifically. So moving on into the 5G of geometric deep learning, which is how we also called our contribution, we will be looking at what this blueprint does over some very special input domains omega: grids, groups, graphs, geodesics, and gauges, which also mean images and sequences in the case of grids, homogeneous groups like spheres, and the graphs and sets, and also manifolds, meshes, and geometric graphs. And throughout CS224W, the focus that you had was primarily on the domain of graphs. And as a result, this will be how we focus the rest of the lecture. So we'll first see how GNNs specifically fit within this paradigm, which might involve quickly rederiving or reintroducing some things you've already seen in the course. Then we'll see how you can use it to expand GNNs into other domains, and it might give you insight into the world beyond, or how to design GNNs beyond just the simple concept of permutation equivariance. And throughout our discussion, we'll hopefully get enough time to cover many architectures you heard of before, like transformers, CNNs, or even deep sets or spherical CNNs. So these will be the architectures that we will roughly be studying today. And I will first start by recapping what you've already seen in this course. So the geometric deep learning perspective applied specifically on graphs. So we'll start off actually with an even simpler case where we have a graph with no edges. So our domain omega is just the set of nodes. And as before, we will be featurizing the domain. So let xi be the feature vector of the ith node. As you already know, we can stack them into a matrix of shape n times k, where the ith row gives you the features of the ith node. And by the very act of doing so, you've specified an order of the nodes, and you'd ideally want your neural networks to not depend on this. So what we want is, if we have a function, a neural network applied over this set of points, giving us some outputs, we want that output to be the same, even if I decide to perturb the order in which I present to you these different nodes. And it's very useful to think about what are the operations that will change the node order. And as you know, these operations are known as permutations. For n nodes, there's n factorial many of them. And in fact, because the permutation is a linear group action, we can identify a unique n by n matrix, as discussed before, which is associated with every permutation. And we call these matrices permutation matrices. I've given here one example of one for the permutation 2413. And the only effect they have is that when you left multiply them with a particular node feature matrix, it only perturbs the order of those nodes and leaves everything else unchanged. So it's a very nice way for us to reason about any kind of meaningful transformations applied over the node feature matrix. And once we have this concept of a permutation matrix, defining a permutation equivariant model is quite easy. So if we want to design functions, neural networks f of x over these node features that will not depend on the order, it's the same as saying, if I apply a permutation matrix, that shouldn't change the outcome. And this gives us permutation invariance by directly following the blueprint that I showed you before. So no matter what permutation matrix I choose, my function f is permutation invariant if the output is the same, no matter what I do to the input in terms of permuting it. And one very generic function form f, which satisfies this, is the deep sets model proposed by Manzel, Zahir, and others at NeurIPS 2017, which transforms every node in isolation with a neural network psi. And then there is a permutation invariant aggregator, which sums them all up together. And then there's a additional neural network phi at the output that can transform the output into whatever you care about. And the part which is critical, which makes this permutation invariant, is the summation. Because summation is permutation invariant, it will be the same no matter what order I choose to permute my nodes. And this also implies that you can do other aggregation functions like maximizing or averaging. If you want to not predict at the level of entire sets, but predict on the level of individual nodes, well, as we mentioned, permutation invariance is not necessarily what you want, because the invariance will destroy the identities of individual nodes. So instead, you might be interested in functions that don't change the order of the nodes. So if you permute them, it doesn't matter if you did it before or after applying the function. And this, once again, by directly following the blueprint, gives us permutation equivariance as a condition on the function f of x, such that no matter what permutation matrix I use, if I apply it before the function, it is the same outcome as if I first applied the function and then permuted. So if I have this concept, I can just stack a bunch of these equivariant layers to transform the information in my nodes. Now, if we want to go beyond sets to the domain of graphs, well, it's actually very simple. We don't now just have a set of nodes, we also have a set of edges between them. And there's many ways you can choose to represent these edges. I choose to use the adjacency matrix just because it's a linear algebra term, and I'm trying to stay within the realms of linear algebra. So imagine I represent my connectivity between the nodes with a matrix A, which is binary. So it's 1 if there exists an edge between I and j, and 0 otherwise. And you can add other things like edge features and so on, but I deliberately ignore them for simplicity. The maths is still exactly the same, just a little bit more complicated if you choose to add edge features. But what's important is that the main desiderata, which we had on sets, so permutation, invariance, and equivariance, are still there. So the only thing that's changed now in this picture I drew before is that now my nodes come attached with some kind of graph structure, which is also part of my domain. And I would like the output of my function f to be the same regardless of how I choose to present the nodes and the edges. So the concepts that we derived on sets pretty much straightforwardly transferred to graphs as well. So we have both invariance and equivariance defined in the same way. Invariance meaning you're resistant to the application of permutations, and equivariance meaning that permutations affect the input and the output in the same way. The only difference is that now, because graphs have a non-trivial domain part in their edges, the edges now must also be an input to the function. And as a result, whenever you permute the nodes, you must also appropriately permute the edges. And since the adjacency matrix is an n by n matrix, and both the rows and the columns correspond to the nodes, whenever you apply a permutation matrix P to the nodes, you must also apply it to the rows and the columns of the matrix A, giving you this convenient form of PAP transposed, which is the effect of applying a permutation to the adjacency structure. So with that in mind, the invariance and equivariance formulae are pretty much exactly the same as what you've seen over sets. There's just that extra input that you have to be mindful of. Now, another thing that I mentioned is quite beneficial by the geometric blueprint is we want to be able to design geometrically stable, i.e. local equivariant layers. And the graphs give us a very nice context for this locality, which is a node's neighborhood. So for a node I can define its one-hop neighborhood as the set of all the nodes it's connected to with an edge. And I can also extract the set of features in the neighborhood, which I denote x and I. So these are all the feature vectors in node i's neighborhood. And now I can define my local function as one that operates over this particular multiset. So features of a node and all the nodes in its neighborhood. And now you can build permutation equivariant graph functions by just applying this local function over every neighborhood in isolation, as you've seen time and time again in this course. And the only thing I need to make sure that this f is now equivariant to permutations is that G is resistant to any order you choose to present the neighbors. So if G is permutation invariant, F will be permutation equivariant. Now, this has been mostly a recap, but I have used a lot of mathematical terminology to rederive everything and make sure we're on the same page. And I just thought it would be very nice to give also a pictorial representation of everything I've told you so far. And here I have, the recipe for graph neural networks fully visualized, right? So my local function G is applied to every single node neighborhood in isolation, and it takes the features of a particular central node, XB in this case, and the set of features of all the nodes that are immediately adjacent to that node. And as a result, applied over that entire set, it derives the updated features H for that particular node. And once you have a GraphNet, which is designed like this, you can take your input graph specified by some node features and adjacency. You get updated features in every node that's somehow parameterized by the locality around that particular node. And once you have these latents, what can you do with them? Well, you can do node classification, so stay equivariant until the end and just attach a classifier. You can classify entire graphs, but as we discussed before, you need to do this in a way that's invariant to the permutations of the nodes. So you need to perform some aggregation of all of the nodes, which is permutation invariant. So here I've given this O+ to represent anything which could be sum, max, averaging, or anything like this, and then attach a classifier to that combination. And lastly, unique to graphs, we also have the notion of an edge, on which we can define also prediction tasks over those edges, or even we can predict existence of edges, which would give rise to link prediction. So all of this should be reasonably familiar. And in fact, specifically, I haven't told you anything about how to define these individual layers. And that was largely what Jure was teaching you in the previous lectures of this course. But I'll just try to give you a very quick overview of how I like to categorize them. So we can roughly partition most of the proposed architectures that act on a locality of a neighborhood by the convolutional flavor, which would encompass models like GraphSage, GCN, and SGC, which have pre-computed and stored coefficients of interaction. We can learn those coefficients by attention, giving us models like Monet and GAT. And we can also do the full-blown message passing, where both nodes collaborate together to predict the message vector to be sent across. And this is what's used in interaction networks, MPNNs, and DeepMind's graph nets. So this is a very speedy run through of GNNs and kind of casting them back to the framework of the geometric perspective and permutation equivariance. And now I want to show you how all permutation equivariant neural networks derived in this way can be seen as special cases of GNNs. And this is actually a good point for a short, maybe no more than 5-minute break, because like so far I've covered material that is known and I've kind of cast it back to the blueprint and the notation that I was using. So are there any questions at this particular point? Because understanding everything up to now is going to be important for what happens next.
Thank you, Peter. This was great so far. Really nice kind of overview, summary, and bringing it all together. And we have some questions. I'm going just to read them and you can respond. Somebody's asking, I'm not quite sure what is the meaning of being geometrically stable with respect to graph. Could you give us an example of what is the distorted image of a graph?
Yeah, so one very obvious example is that, and I'll cover this very shortly, is that the edges that are given to you in the graph may not necessarily be God-given. They may not be ground truth edges because there's noise in everything. And as recent work on adversarial GNNs shows, you can actually carefully perturb only a handful of the edges and make GNNs totally confused about what the outcome should be. So one natural example of distortion is we don't know what's the graph structure necessarily.
Okay, thank you. So you are thinking about kind of distortion of the topological structure of the underlying data, so of the underlying graph.
Yeah.
Super. And then the next question, also super interesting. Do you know of any problem or a domain where the assumptions you make break down? For example, where we do not necessarily want our models to be equivariant, invariant, under small perturbations, translations, or rotations?
Mm-hmm. So this is a very interesting question. And I will say that usually when these kinds of assumptions break down, you can enforce the symmetry breaking by giving specific features that tell each node what its coordinates are. And we will see this when we talk about transformers in a little bit. But essentially, you can keep the, the nice geometric properties of the model itself, so to still have a more tractable problem, but you can modify the features of your problem so that the model can make advantage of this symmetry breaking information if you have it.
Exactly, which is like, for example, in the class, I think if I connect it back, it's about position aware or IDGNN and things like that, right? Where you have some positional information.
Yes, this is exactly what I was thinking of. Yeah.
Awesome, awesome. Super. I think this was a nice short break and very insightful questions. I think let's get into the second part.
Yeah, sounds good. Okay, so let's talk about how we can use everything we've discussed so far to relate all permutation equivariant neural networks to GNNs. So basically, Before I try to go beyond permutation equivariance, I want to give a brief note on how all these blueprint restrictions can help us immediately take any permutation equivariant model and relate it as a special case of a GNN. And how I'm going to do that is, as my answer to the recent question hinted, we've assumed something seemingly very innocent so far, that the graph is given to us. But in practice, even if we have a graph, it may be suboptimal for the problem you're solving. For example, I'll just give a quick example from theoretical computer science. If you want to do connectivity queries on graphs, so I give you two nodes and I ask you, are they connected? If you maintain the original set of edges, you can easily come up with a degenerate case where the nodes are arranged in a path, and predicting their connectivity requires a linear amount of layers to cover the entire path. But if you carefully choose a different set of edges mandated by a particular data structure known as the disjoint set union, you can actually answer these questions in amortized constant time. So the choice of edges, even if they both represent the ground truth structure, can be quite critical for the complexity of solving the task you have. And we can take it to the extreme, right? There's irregularities in the graph itself, but what if I don't give you a graph to begin with? So imagine we just have a node feature matrix, but there's no adjacency. And to cover what I want to do in this section, I'll just briefly assume two very special case solutions. The first one, when nature doesn't give you a graph, is you can just bite the bullet and assume that there are no edges to begin with. So assume there's no connectivity between the individual nodes. And this means you're just transforming every node in isolation with some shared layer psi. And this gives exactly the deep sets model, which we already discussed. So deep sets can be related to a graph network in a specific case where we assume the neighborhood to be just the set containing the node itself, and that's it. What happens when we flip it back to the other extreme? Let's just assume everything is connected and let the graph neural network figure out what are the edges that matter. This is a very common strategy, often employed in models like interaction nets and relational nets. So here, my neighborhoods Ni are assumed to be equal to the set of all the nodes. And it turns out, and this is a great exercise for you to show afterwards, if you use a convolutional flavor of a GNN, like a GCN, this doesn't make sense actually in this setting, because you'll end up with a model that's equally expressive as the deep set model. And it's a great exercise to try to show this. But OK, let's then try to step up the complexity by one level and instead use an attentional model. So let's have a graph neural network given here in the bottom left corner, where I aggregate over my neighbor node features, and now neighbors are the entire set of nodes. And I have a learned attention function between the two nodes, which tells me the coefficient of interaction. And does this look familiar? This should hopefully look familiar to some of you. In fact, I have just described to you a transformer. So just by doing the appropriate reduction on a particular setting of a fully connected graph in attentional flavor, I have re-derived the transformer as a special case of an attentional GNN. And the only thing, and this is also related to a question that I just answered, the only thing which makes the original NLP transformer special in terms of its structure has nothing to do with its architecture. It's to do with the fact that you inject positional embeddings, which tell you roughly for every node where it is in the sequence. If you were to drop them, you'd have equivalently a fully connected graph attention network. And you can see the inference of this attention coefficient as a form of soft adjacency matrix. I don't have a lot of time to dive into this connection, but I think it's really fascinating. And if you want to learn more about it, Chaitanya Joshi has written a really nice article in The Gradient about it. So I highly recommend checking that out. And just one brief remark, because I don't have enough time to stick around for this setting, but I think it's very important. The empty graph, as mentioned, ignores a potential wealth of information. If your task is at all relational, then it's a bit cursed in this setting. The full connected graph is very powerful, but can be quite hard to scale because it's quadratic complexity and has large neighborhoods, especially as you increase the number of objects. So the truth, the ideal, is likely somewhere in between. We want to figure out the adjacency matrix, that's the true one, and then use it as the edges for a GNN. This setting is commonly termed latent graph inference, and it's super tricky because choosing the edges is a discrete decision, so it's inherently hard to do backprop through them. And unfortunately, it's out of scope of this lecture, but I've left some pointers to interesting models like NRI, DGCNN, DGM, and PGNs if you want to learn a bit more about what kinds of things have people been proposing in this particular area. So we have now covered GNNs and also showed how other permutation equivariant models like deep sets and transformers can be related directly to GNNs just by using the special cases prescriptions of the blueprint. Now I want to dive into more interesting geometry, and particularly I'll start with an old friend, the convolutional neural network, and see how looking at them through the lens of Fourier analysis, we can relate CNNs to a very popular class of GNNs known as the spectral GNNs. And hopefully this will give you some more perspective on how GNNs have historically been constructed, and maybe also some inspiration for the future. So if you've done any kind of digital signal processing previously, you might be aware of the convolution theorem, which is a very attractive identity, which says if you want to do convolution over a particular domain, if you can first turn it into the frequency domain by some kind of Fourier transform, your convolution becomes just pointwise multiplication. And pointwise multiplication is quite easy to implement, and it could give you a detour to defining a graph convolution. But the problem is, what is the graph domain? How do we use it properly in this setting? So in order to make that connection, I'll actually first show you how graphs happen in the case of discrete sequences like grids and images, where this Fourier connection is much easier to realize. So as you probably are aware, grids like images, text, and speech can all be seen as a graph. You just have these different pixels in the environment, and they're connected to their immediate spatial neighbors. So now you might ask yourself, what would a graph neural network look like in this case? Well, you can make a simplifying assumption to make it very easy to work with, which is a cyclical grid, where you connect the edges to the other side so that you avoid nasty boundary conditions. And now you actually have that every node has identical structure and degree, which allows you to define a proper convolution over neighborhoods, because every neighborhood locally structurally looks the same. So you can have a filter that you just slide across. And one thing that's very different is that now every node can be identified with its position on the grid, which gives you a much stronger translation equivariance requirement compared to the permutation equivariance of graph nets. So as mentioned, you can imagine sequences as organized in this cyclical grid graph, and a convolution network usually looks at some locality neighborhood around a particular point. So here you have one particular convolution that looks at point x2 and points x1 and x3 around it and multiplies with some specific coefficients for the left neighbor and the right neighbor. And if you represent this operation in a sort of matrix form, you'll realize that the matrix that you're multiplying with your node features is of a very special form. It is known as a circulant matrix, and it has this very special structure where every row is a shifted version of the previous row. So you start with like A, B, C, and then at every layer you shift it cyclically to the right by 1. And when you multiply this matrix of coefficients with your node features, you'll end up with exactly the result of convolving with that particular 1D filter. One thing that's very nice of these special circulant matrices is that they commute. This is a very fun property that you can try to prove. So no matter what parameter vector I put inside these circulant matrices, it doesn't matter what order I apply them in, and I'll get the same result. And another well-known fact from linear algebra is that matrices that commute can be jointly diagonalized. That means that eigenvectors for one of them will be eigenvectors of all of them. And so that means actually conveniently that all circulant matrices have exactly the same set of eigenvectors, and they turn out to be exactly the basis of the discrete Fourier transform. And you can show this by just taking the special circulant matrix of 0, 1, 0, 0, 0, and so on, the so-called right shift matrix. And when you take the eigenvectors of the shift matrix, you'll end up with exactly the discrete Fourier transform. So this is a particularly attractive property because now if we can stack these Fourier basis vectors into a matrix, we end up with exactly the discrete Fourier transform by multiplying with the conjugate transpose of this matrix. And because this is an eigendecomposition of any circulant, that means you can represent any circulant matrix as this standard eigendecomposed product of phi lambda phi transpose, where lambda is now just the diagonal matrix of the corresponding eigenvalues. And now from there, you can derive the convolution theorem fairly directly. So imagine you have a set of node features X that you want to convolve with a circulant matrix C. You can represent C as its eigendecomposition, so phi lambda phi conjugate transpose. And then what you do is you first take the discrete Fourier transform. So you take X into the Fourier domain by multiplying it with phi star. And then after that, you have to multiply just with lambda, which is a diagonal matrix of eigenvalues. So you've reduced convolution to pointwise multiplication with the Fourier coefficients. And this is really cool because this is something that holds for every single convolution. All convolutions are circulants, therefore every convolution has its own unique set of Fourier eigenvalues. And what this means is that it's given us a very nice spectral detour. If for any reason we don't want to perform the convolution by multiplying with a circulant in the spatial domain, we can instead first take the Fourier transform, then take a pointwise multiplication with the corresponding eigenvalues, and then do the inverse Fourier transform to get the same result. And the key idea here is that you don't need to know what the original convolutional filter was if you know what are its eigenvalues with respect to the Fourier basis. So this is one very impactful idea that we can use to potentially try to define graph convolutions. On graphs, convolutions are obviously going to need to be more generic than circulants because graphs are more complicated than grids. But you can still use this concept of sharing an eigenbasis. So if you know a particular phi matrix for that particular graph, you can only focus on learning the eigenvalues. So for grids, we wanted to commute with a shift matrix. But in the case of graphs, you can just replace the shift adjacency matrix with any adjacency matrix of your graph. So the main thing that's different is that on different graph problems, the structure of the graph will be different. So every graph will need to have its own phi matrix at this particular point. Now, the problem here is that you want to commute with the adjacency, but adjacencies cannot always be eigendecomposed. So instead, we will use the graph Laplacian matrix, which you might have seen in some papers like the GCN, where you just take the degree matrix minus the adjacency. And as you can see, it actually, if you see it for a particular example graph, it captures all the important adjacency properties of the graph, but in a way that you can now actually eigendecompose it. So now you can re-express the Laplacian matrix as, once again, phi lambda phi star. And any operation that commutes with the graph structure can be expressed just by changing the eigenvalues in the matrix lambda. And this is commonly referred to as the graph Fourier transform, which was one of the pioneering papers on graph neural networks from Jean Bruna in 2014. And once again, you can, to convolve with some particular node feature matrix, just multiply with the conjugate transpose of phi, multiply pointwise with the eigenvalues, which could be learnable, and then map back to the spatial domain by multiplying with phi. Now, the problem is that you cannot really directly learn the eigenvalues in most cases of interest because they're not localized. Just like in a usual Fourier transform, every node will influence any other node. It's very strictly tied to the graph structure, so it won't generalize to other graphs. It's computationally expensive to eigendecompose, and so on and so on. So instead, a very common approach is to force the eigenvalues to be related to the eigenvalues of the Laplacian. And usually you force them to be related by some degree k polynomial. And this actually is quite convenient because this whole expression we had before just turns out to be a polynomial of the Laplacian times the node features. And depending on the choice of the polynomial, like cubic splines, Chebyshev, or Cayley polynomials, you end up re-deriving many standard classes of GNNs, including the popular Chebyshev networks of Michael Deferard and others. Now, one thing that's very important to note is the very fact of you saying you're going to use a polynomial in the Laplacian means you've defined the convolutional GNN, because you can pre-compute the coefficients with which your nodes are going to interact. And many efficient spectral approaches, to make themselves efficient, will turn themselves spatial in very similar ways. And that means that in many earlier papers, including my own graph attention network paper, you might have seen the statement that graph nets can be partitioned into spectral and spatial. Well, this divide is actually not really a divide, and I was also personally wrong to state this. In most practically useful cases, spectral GNNs are actually going to be very special cases of spatial GNNs. And I'll just briefly go back to the transformer for a second, because if you have read the original transformer paper, you might have seen that it gives the positional embeddings as these sort of sequence of sines and cosines that are related to the position. And in fact, these are very similar to the eigenvectors of the discrete Fourier transform. So you can think of these positional embeddings as basically eigenvectors of a graph Laplacian for a grid graph. It's hinting to the transformer that it's located in a grid structure. And we can actually use this idea to then generalize transformers over more generic graph structures. Just take whatever are the eigenvectors of the respective graph Laplacian, i.e. the columns of our phi matrix, and feed them as extra node features. This idea was initially popularized by the graph transformer of Duedy and Bresson. But if you look at some very recent times, this is a super emerging area of research. I think there's been like 4 or 5 graph transformers proposed very recently. So it's a very interesting direction to consider for the future, and potentially for some of your projects if you're interested. So using the Fourier connection, we have derived how we can talk about generic graph convolutions by generalizing the spectral analysis of image convolutions. Okay. Now, I want to emphasize another really cool connection where we will run away from the domains that we know and love and easily work with in deep learning. I'm actually going to try to redefine some aspects of a so-called spherical CNN. So I'm going to talk about convolutions over domains that are more generic than just grids. And to make this thing a little bit more easier on the maths, I will switch from discrete to continuous, but no matter what I conclude in the continuous domain, it will carry over to discretizations. So imagine I have a Euclidean domain where my data just lives on the real number line. So every point on the real number line has some features attached to it. And convolution on the real number line has this familiar form, which you've seen before in many other courses, I'm sure. It can be expressed, the convolution of the signal x and some filter psi, as an inner product of the signal x and some appropriately shifted version of psi. And the parameter of the shift is the input to the convolution. So the output of this grid convolution takes different shift values as input, and therefore it's another function over that same grid. Now, one very important finding is that this will not be the case for every single domain. And what we will see now is how we can take this idea and generalize it to more general symmetry groups. So more generally, if we have two signals that are defined over a domain omega, we can define their inner product if we have an appropriate metric to integrate with respect to. So we can take two signals, x and psi, which give you features on different points on omega, and take their inner product by just integrating over the domain the corresponding pointwise products. Okay, so here on the top, you have the example of this in the case of grids. And now, in the case of general groups, what do I want? I have two signals, x and psi, which are specified with respect to some symmetry group G. Well, that means if I want to take a particular group action G, I take the inner product of my signal with the appropriately group transformed signal psi. So previously, my group action was the shift. Now I have a more general set of group actions that I need to be respectful with. And that means in this integral form, I'm taking now the integral of the pointwise products of x of u and psi, checking what point will end up on u, which is basically the inverse transform applied to the domain point u. So one thing that's important to note is that generally speaking, when you perform a convolution with respect to a symmetry group, it will be a function over g's, over individual elements of the symmetry group. Now, when we were doing grid convolutions, this was totally fine because elements of the shift group are themselves real numbers. So as a result, you could take a function on the reals and get another function on the reals. But in more general cases, we will start with a function that could be over our initial domain and end up with a function that takes inputs over our group. And this is a very important concept that we will now use to try to define convolutions over the sphere. So imagine a domain, omega, which is the sphere, and we want to create some convolutional network over it. This is a very relevant domain, by the way. Maps of the Earth naturally live on a sphere. Signals that we get from astrophysics, like cosmic microwave background radiation, are often represented as spherical signals because they're captured by detectors on the surface of the Earth. And when we have a neural network applied over the sphere, we want it to be rotation equivariant, right? No matter how we rotate the sphere, this is still representing the same signal. And that means we need to use the special orthogonal group SO3, which is the set of all 3D rotations. And as you can easily see, image CNNs cannot cope with this kind of requirement because no matter how you project the sphere into a plane, as you start to get closer to the poles, your CNN filter will look very much distorted and it will not respect the rotational requirements. So, okay, let's try to apply the group convolution idea, which I put in the bottom right, in the upper right corner, just as a refresher if you need to check it as we go along. So in this case, we can represent points on a sphere, our domain elements, with three-dimensional unit vectors u. And our group actions, which are the rotations, can be represented using 3x3 orthogonal matrices R. So what does our spherical convolution look like? So we have a signal over the sphere convolved with another signal over the sphere. And now it's parametrized by a rotation matrix R. And we take the inner product of the original signal and the appropriately transformed filter psi. In this particular case, in order to do the appropriately transformed filter, the point that will line up at U is the same point that is the inverse rotation of U. So we take this transformation, and just by following the group convolution blueprint, we end up with our spherical convolution. But you see, our initial function was applied over these three-dimensional unit vectors U. The output of a spherical convolution is defined over SO3. Its inputs are 3x3 matrices. So I cannot just do the standard deep learning thing of stacking more layers, because my first layer acted over 3D vectors. My second layer would need to act over 3x3 matrices. Now, luckily, we can use a very standard trick, which makes our blueprint still work in this case, because we can always define a group action of the group over itself by just composing the two corresponding actions. So in this particular case, I apply a symmetry group action G over a group input H by just composing G and H together. So I can perform the outcome of the group action just like before. So we can always build these G equivariant layers over G itself. So what this means is that our spherical CNN will start with a spherical convolution at the input layer. And then every layer after that will be SO3 convolution over SO3 itself. So let's just spell out the maths of what's happening here. As I mentioned here, we have this group action, which takes one group element and transforms it using another one. And in this case, these G and H will be rotation matrices. So it will end up with R inverse times Q for 2 rotations. And if you look at the expression for what the group convolution is, which I've copied here just for convenience, we can now put this all together and derive a 2-layer convolution over spheres. So we had initially a signal over a sphere X convolved with a signal over the sphere psi, which now altogether gets convolved with a signal over SO3, which is phi. And that is an SO3 layer giving SO3 outputs. So it will be parameterized by rotation matrices R. And what we do is we take the output of our first convolution defined in some matrix Q, and we see where our filter phi would line up at that point Q, which is R inverse times Q, just like we did before. And we integrate over the entire domain of 3D rotation matrices. And this general idea of taking the spherical layer and then stacking SO3 layers is the essence of the spherical CNN, which won the Best Paper Award at iClear 2018. I have omitted the specifics of how this layer is actually implemented. There are some really clever computational tricks that allow you to do this very efficiently in software, but I wanted you to sort of have a feel for how the mathematical principles of a model like this relate to the group convolution that we just discussed. And one very important thing to note is that no matter how many integrals and shifts and transformations I've done here, you can still relate the spherical CNNs to GNNs, because in practice, you want to do local filters that are geometrically stable. And the sphere itself, you cannot feed a continuum of data into a computer. It must be discretized to take many points on the sphere. So this filter psi will be local, and the sphere will be a discretized set of node features. So you can think of the non-zero elements of the filter, which is local, as the immediate neighborhood of a particular point on the sphere. And therefore, computing this integral is actually very similar to message passing, because you'll be taking a sum over all the parts where psi will not have a 0 point. So basically, the local neighborhood of a particular point on the sphere. And what's really cool is that this G convolution over G approach works over any global symmetry group G. This is something that in principle you can do always. Now, there are 2 caveats with this. First of all, it's only really tractable to do this over very small groups. So SO3 convolutions worked because SO3 can be described with just 3x3 orthogonal matrices. It may be tempting to try to take this idea and apply it to graphs, but if you want to do permutation group convolutions over the permutation group, you're going to need to maintain n factorial entries, because that's how many elements the permutation group has. Now, this is obviously an important result for making it intractable for graphs, but it also hints that there are many, many interesting graph convolutions, so layers that will perfectly finally commute with your graph structure, that will not be captured by our previously simple idea of let's just aggregate one-hop neighbors around each node, though this idea likely captures the most tractable graph nets. And some of these graph convolutions that we haven't discussed before in the course may in fact trade off, how expressive they are versus how stable or how complicated they are to compute. And it also suggests a way out of, the most expressive GraphNet issue and the Weisfeiler-Lehmann hierarchy. Effectively, there could exist many, many graph convolutions that are defined in a more complicated way that allow you to escape this notion of just passing random hashes over edges of a graph. The second very important caveat here is that both the sphere and the circular grid are so-called homogeneous domains, which means effectively that any 2 points on the domain look the same, right? Every point on the sphere kind of locally looks the same like any other point on the sphere. This, of course, does not hold on graphs. When we did this on spheres and grids, it allowed us to basically, define a nice geometric spatial filter and just slide it across the domain to build convolutions. And the last question I would like to try to answer in this lecture is what can we do in the more general case when the domain is not homogeneous? So we've covered through the lens of spheres how we can define convolutional networks over groups. And now I will talk about the last architecture for today, which will concern geometric graphs and by connection geodesics and gauges. So let me go back to graphs for a second. So far, and I think very often throughout the course you've assumed that your graphs are a discrete, unordered set of nodes and edges. But in many cases, this is not the whole story. In fact, the graph could have some spatial geometry attached to it because it comes from an underlying spatial process. And it will, of course, be very useful if your models can make advantage of this geometry. One classical case of this are molecules, because in principle, molecules are not just a random unordered correction of atoms. They actually have a very clear spatial conformation, and therefore every atom can be endowed with some x, y, z coordinates, and there could also be angles between them, and so on and so forth. This, of course, becomes immensely more complicated when you go beyond small molecules and into the domain of proteins, where models like AlphaFold tend to shine. So let's just consider a very simplified geometric graph setting where my nodes no longer just have, general scalar features, but they also have three-dimensional real coordinates, and I'm explicitly delimiting them. So the features are f and the coordinates are x. And if I have an equivariant message passing layer over them, I'm basically going to be transforming them separately. This will give me updated features as well as updated coordinates for every node u in the graph. So now, once we have these geometry and these coordinates, we can express what's the symmetry group we want to be resistant to. And one common group to be resistant to in the case of molecules is the Euclidean group E of 3, which contains rotations, translations, and reflections. So no matter how you rotate, translate, and reflect the molecule in space, it is still representing the same molecule. And these group actions are very conveniently represented by multiplying the coordinate features with any 3D orthogonal matrix, followed by any particular affine shift. Okay. So just like we designed permutation equivariant GNNs, we can now also design GNNs that will obey E of n equivariance, so n-dimensional Euclidean equivariance. And one very elegant solution to this was recently proposed by Victor Garcia, Satoras, and others, and was published at ICML. And it does a very simple modification to how the features f are transformed. So our message function now takes into account the features, the flat features of nodes u and v that are linked by an edge. And we add just as an extra feature the distance between the two coordinates. And we have a similarly defined layer which transforms coordinates into updated coordinates. Here, psi and phi are learnable MLPs. Now, what's very important is that when you parameterize the layer in this way, any action of the Euclidean group will not change the distance between the nodes because these actions are isometric. So if I were to transform my coordinates by applying the E of n group action, the f prime will not change as a result, which is exactly what we want. And further, if x prime, the updated coordinates are defined in this way, they will transform exactly according to the symmetry group. It's a nice exercise to verify this, and it will be exactly as expected. So this layer gives you E of n equivariance in a super elegant way. You just have to modify the message function by adding this extra input over any scalar features f of u. Now, this is all great, but very often we don't have just this simplified case of scalar features and coordinates. Sometimes also some of the node features will depend on the geometry. For example, you might want to represent forces that act on every single atom in the molecule. And these forces are typically vectors in the underlying Euclidean space. So whenever you rotate the molecule, you need to also accordingly rotate the vectors. So here, for example, if you have a field defined over an image which has vectors on it, and you rotate it by 90 degrees, the scalar heat map doesn't change in properties, but the vector orientations do change. And the previous model that I've shown you would not take this into account. Now, the authors of the GNN paper do propose a variant that will work also with vector-based features. But as you keep tensoring up, like going from vectors to matrices to tensors in the original space, like this issue will keep reappearing, and every time you'll have to fix it. So it might be interesting to think about, can we talk about what's the general set of solutions that will always give us this equivariance that we want? And to arrive at the general solution, we can consult some other relevant work like tensor field networks that actually realize that you can parameterize any group action of rotation and translation as an appropriate change of basis matrix Q, and then apply this so-called irreducible representations known as the Wigner-D matrices. Now, I cannot go into details of how they act because it's way out of scope for this particular talk, but you can exploit the fact that these matrices can be pre-computed for the SE3 group, and then directly plug them as transformations inside a message passing model, where now features of a different dimensionality exchange messages with features of all other kinds of dimensionalities. So you have scalar features, vector features, matrix features, and so on, and they all combine together in this kind of convolution from K order ones to L order ones. And the matrices that govern the interaction between them are pre-computed based on these Wigner matrices above. And this idea is then further expanded to the realm of graph networks with this fantastic paper on SE3 transformers from Fabian Fuchs, Daniel Worrell, and others. And in this particular case, they just take the idea of tensor field networks, which worked over general point clouds, and restrict it to only act over neighborhoods, much like a graph net would. And they also add support for the transformer attention. So this particular layer will allow you to tensor up as much as you want, and it will still give you correct outputs, but you still need to pre-compute these W matrices that give you the interactions. So in a nutshell, you have a particular point cloud over which you define a graph representation based on, say, nearest neighbors. You pre-compute these weight matrices based on the solutions for the SO3 group. And then using those matrices, you can perform transformer aggregation or any kind of message passing and aggregate the results accordingly. Now, I'll just say that working over these geometric graphs is a case over which can also be derived by going in the opposite direction by starting over geometric manifolds, which are general domains like the human body, the meshes, and fMRI signals, and so on. They can all be expressed as manifolds. And in fact, what you can end up deriving is that all of these manifold-oriented models will be not at all dissimilar to what we just talked about in equivariant message passing. I've deferred all the detailed exposition and theory to our draft book if you want to read more, because we don't have enough time in this talk. But I'll just briefly mention that the key concept that these models rely on is known as parallel transport, where you want to do a convolutional filter, but your domain is not very nice and regular and homogeneous. Well, you can use parallel transport to transport the filter from a point to another point, so you can apply a convolution. Now, the big problem here is that the parallel transport is path dependent. Deciding in what direction you move the filter will potentially give you different results. To illustrate this, on this particular manifold input, you can actually define sliding a filter, like this convolution filter here, over the surface. And you can go from the mouth to the right ear by just following the shortest possible path, and it will give you a filter oriented like this. But you have to be careful. If you chose a different path, like the one which goes first to the top of the head and then descends down to the ear, you'll actually end up with a filter that looks different. So you have to be careful and principled in how you define these different transport operators. But that still didn't stop many authors from coming up with clever architectures that directly use this blueprint to derive mesh-based convolutional networks. And some popular works here include the geodesic CNN and the gauge equivariant mesh CNN. But if you were to peer into the equations of some of these complicated layers, you'll actually see that they are very much like message passing. The main difference from a standard GraphNet and what the gauge equivariant mesh CNN is doing is that for every 2 neighboring nodes on a mesh, it pre-computes this group action transport matrix, which transports node V to the node U, And this is something that can be pre-computed based on the structure of the mesh. Once you have that pre-computed, you're basically just doing a graph neural network over the geometry. So hopefully this also gives you a way to link back what's going on in traditional permutation equivariant GNNs to GNNs that act over more generic graphs with geometry information attached to it, and then further how there's a very deep connection between them and all of these specialized CNN models that act over general manifolds like the human body given here. So before wrapping up and going into Q&A, I'd just like to give you a few interesting further resources if you want to study the field further. So all of these findings that we did are summarized in our proto book on geometric deep learning, and you can find all resources, blog posts, talks on geometricdeeplearning.com. Though I did give you today a very much different overview that I would give to most other audiences, because I'm talking to a group that already covered graph nets, so we could do a lot more exciting stuff than I would normally do. But if you're interested in a few other expositions that maybe take the graph part a bit more slowly, there are also some interesting keynotes and that you can look at there. We have a 156-page proto book on the archive, and we are hoping to get the full book published by MIT Press sometime next year. And we also gave a course just on geometric deep learning at the African Masters in Machine Intelligence, and we have made all 12 hours of lectures and many other associated materials, collab exercises, and so on publicly available on our website. So do check that out if you'd like to know more about any domain specifically in a 1-hour targeted setting. And that was actually my last slide. Thank you so much for listening. I'd be happy to take any questions. And if you have any questions offline, you can also reach me via email or via my various social networks. And before concluding, I'd just like to thank all of my book co-authors, Joan, Michael, and Taco. And once again, thanks so much, Jure, for giving me the honor and pleasure of presenting to this group today. Thank you so much.
Yeah, thank you. Thank you so much, Peter. This was awesome. The right topic at the right time, really great. We have a few minutes for additional questions. I'm going to read a couple, and if students have more, just go ahead and ask. The first question is, can we apply these spatially aware techniques to robotics? For example, where nodes represent joints and edges represent limbs, the nodes might even have features such as net force vector experienced by the joint.
Yes, very much so. I haven't seen any examples of this actually applied on real robots, but I will say that it has been extensively applied in simulation. So in domains such as Mojoko or something like this, there were these impactful papers like NerveNet that explicitly parameterize the joints of the agent as nodes in a graph, and they actually run a graph neural network over the spatial representation to decide how to move every joint. So it also allows you to have not just a graph structured input for the RL problem, but also a graph structured policy. You have a different action for every node over your robotic agent. So while I haven't seen any like real robot applications, I have seen a lot in the simulation domain that could be applied to robots.
Super, because that's very relevant, because the student was then saying, you know, one thing you could do is to, for example, predict the voltage to apply to the control robot of every joint, you know, I know, for a robot to learn to walk. And that's kind of essentially what you also said is one direct application of this.
Yeah, so my suggestion would be to check out the NerveNet paper. It is a very nice simulated application of what this question is asking.
Super. Thank you so much. Another question that I think would be interesting is, could you talk about future evolution or development of the field, and you know, what do you think are big open problems or interesting research directions and areas for the future?
Yeah, definitely. So I think to begin with, the field that I only glanced over in my talk of latent graph inference is going to become a lot more important in the future, because the more you look at, you know, natural problems that are graph structured, very often the graph itself is derived as a result of some heuristic, and often the practitioners that are working with these graphs may just be inherently interested in knowing what is the underlying causal graph structure that I'm looking at. Like, how can I interpret the mechanistic properties of this environment? This is going to become more and more important as we use GNNs to tackle scientific problems. So, you know, getting better at figuring out the underlying graph when there's no graph or when the input graph is noisy, I think is going to be very, very impactful. So that would be one direction that I would really like to see developed more. And another one, which is very important, I think, for generic GNNs is, as you've probably seen in the course on several occasions, this idea of escaping the Weisfeiler-Lehmann hierarchy. There are several very interesting ways to design more powerful GNNs. And one which I find particularly attractive is one where we still do, one-hop message passing, but we modify the graph structure based on some, say, structural properties of the task that we're interested in. So, for example, like these cellular automata graph nets and so on that like invent new nodes for different simplicial complexes of the graph, and then you have message passing between them. So I feel like these structures could be very powerful in designing, very computationally efficient graph nets in only a few layers of computation. And I feel like, we still don't have very nice principled ways of computing these, right? We have many separate papers that say, if you care about this structure, you should pre-compute the graph in this way. If there was something that automatically figures out the structure based on the data, I think that would be a real like silver bullet if we could have something like this.
Yeah, that's an excellent point. Basically, you are saying you could do higher order message passing over higher order structures by, in some sense, inventing new nodes that connect these higher order structures, like you call them simplicial complexes, or in this class we talked about graphlets or motifs. Essentially, it's a very similar idea. Yeah, that's super cool. I think one related piece of work here is also this notion of multi-hop attention that I think would have kind of a similar role, where by inventing a new node, now you can have a more complex type of attention that you can learn over the graph.
Yeah, exactly.
Another question that I wanted to ask you is, what would be your sense is like graphs are these interesting structures where the size of the structure and the amount of information you get, the ratio of that is kind of constant, right? Which is, I would say, very different in text or in images, where you can get multiple images or more text over the same vocabulary, or more inputs over the same kind of data size. But it seems in graph, the information content is proportional to the size of the prediction problem in some sense. And except perhaps in graph classification, where you can get multiple graphs over and over again, in more this kind of one graph type problems, there seems to be some fundamental difference in the way the information comes to the model. I don't know if I ask my question well, but you see what I mean? Like, you can try to rephrase it to see how you understood it.
Yeah. So the way I understand it is basically like in most problems of interest over graph structured inputs, there will usually be exactly one graph or a very small amount of graphs. And it doesn't reconcile as easily with the optimization techniques that we might see in, say, images or even image segmentation, where you have like millions of images, right?
Exactly. Or I can have the same model and train it on 1 million images and train it on 10 million images. It's kind of the same model. While on a graph, I cannot get the same graph, but now get 1 million observations and then get 10 million observations. If I want 100 million observations, I want a 100 million node graph. And if I want a billion observations, it's a billion node graph.
Yeah, this is a very important problem for the area. And, we have to design techniques that are like specific to this one graph case very often to make industrially viable graphs. But one thing that I think is very interesting is how I used to think about these things when I started doing graph learning is, you can think about it as your good old-fashioned traditional deep learning with extra connections between your samples. So I can think of one graph as a collection of a bunch of samples with links between them that tell me that they're somehow related, or that there's a recipe for passing information between them. And that hints at the fact that maybe, you can think of this as basically a way to organize knowledge. And if you can find, related data sets where knowledge has to be organized in a similar way, maybe transfer learning can be one way in which we can bridge this gap. So basically, even if we don't have a nice big label data set for the specific problem we have, we can try to collect gold standard data for related problems and then somehow transfer the knowledge from that GraphNet onto the new domain, like meta learning and so on. Now, I don't know, I haven't worked much on this problem myself, but I think Marenka has worked on this problem quite a bit in the context of biomedical problems. So I think it's definitely an important emerging direction. Yeah.
Okay, super. This was great. Really appreciate the lecture, really appreciate interesting discussion at the end. Thank you also to the students for great questions. Thank you so much, Peter, and good luck with your research. Good luck with the book. And thank you again so much. We are going to share the video with the rest of the class. And really, thank you and good night to UK.
Thank you so much. And thank you so much for having me.
Yeah,
Have a
thank you,
good night.
guys. Thank you. Bye. I just say this concludes the lecture for today. Thank you everyone for participating. We are going to have the last class in person this coming Thursday with some concluding remarks. Thank you everyone for taking the exam. I think you guys did great. Now it's the projects, the quarter end, and then it's the new year. So thank you again so much, and see you on Thursday.